In this video, we are going to discuss basically the converse of the Pythagorean theorem. Now, we're not going to use the Pythagorean theorem itself. Remember, the Pythagorean theorem tells you if you start with having a right triangle, where you know it's a right triangle to begin with, then you're allowed to create this formula of a leg squared plus leg squared equals hypotenuse squared. Our focus in this video is the converse. What if you don't know if it's a right triangle? You have a triangle, you have three sides. Do those three sides make a 90-degree angle or not? And if they don't make a 90-degree angle, what kind of triangle do they make? Do they make an acute triangle? Do they make a right triangle? Do they make an obtuse triangle? Let's start with our first example related to this. Is this thing a right triangle? Yes or no? Well, it certainly looks like it could be. But keep in mind what the Pythagorean theorem tells us. If this thing is a right triangle, and that is probably the worst 90-degree angle I've ever drawn in my life. If it is a 90-degree angle, then we know leg squared plus leg squared has to equal the hypotenuse squared. This equation must be true if it actually was a right triangle. So if the equation was wrong, that tells us it can't possibly be a right triangle. So basically, we're looking at this and our intuition said, yes, this looks like or probably is a right triangle, but it looks like is not a proof. Probably is not a proof. If we want to have proof of it, though, we can go through and take leg squared plus leg squared and verify, does it actually equal the hypotenuse squared? If the Pythagorean theorem actually works, then we can verify this thing truly is a right triangle. And let's get our calculators out then, because I don't want you guys doing 32.5 squared by hand. Let's save ourselves some time with the number crunching. So students helping me out, 32.5 squared is what number? 1056.25. Okay, and 39 squared, then 1,521. And does that equal 48.5 squared? Well, what's 48.5 squared?
2038 or 2,352.25.
Okay, and so when we actually add those things together, this is 2676.25, which is not the same thing as 2352.25. And so although it looks like, hey, this looks like a right triangle, we actually have evidence that no, it's not. If it were a right triangle, the Pythagorean theorem would have to fit. And it doesn't. Using your marker boards, try this one out. What we, of course, needed to verify, leg squared plus leg squared equals hypotenuse squared. Is it actually true? If it comes out to be true, that tells us we do have a right triangle. If it's not true, then it's not a right triangle. So we'll take leg squared, leg squared. Does it equal the hypotenuse squared? Well, 9 times 9 is 81. 12 times 12 is 144. 15 times 15 equals 225. Does 81 plus 144 equal 225? Yes. So yes, this is a right triangle. Just based on some vocabulary as well, please notice that this then tells us 9, 12, and 15. That's called a Pythagorean triple. If you have 3 whole numbers that actually make the Pythagorean theorem work, they're called the Pythagorean triple. They're called a Pythagorean triple. Some very common ones, 3, 4, 5 fits the Pythagorean triple. 5, 12, and 13 fit the Pythagorean triple. And those are really the 2 most common ones. Based on similarity, you can create a whole lot more. So let's continue further. Is it possible for a right triangle to have these 3 side lengths? How is this problem different than the one we had before? The only difference is we don't have the picture. But when we had our last problem, we looked at it and said, well, leg, leg, hypotenuse, does it fit the Pythagorean theorem? Of course, we know the hypotenuse would have to be the longest side, so we're really doing the same work here. Leg, leg, hypotenuse. Will this fit the Pythagorean theorem? Yes or no? If it fits, those 3 things make a right triangle. If they don't fit, it's not a right triangle. That's simple. So let's run through and start crunching our numbers. 10 squared plus 49.5 squared. And since we're using the calculator anyhow, let's do this all in one straight shot. Just type the whole thing into the calculator and see what you get. 10 squared plus 49.5 squared gives us 2,550 and a quarter. So 2550 and a quarter. Does it actually equal 50.5 squared? And so checking that one out, 50.5 squared. Pretty sweet, we see they match. And because they match, we know then, yes, 0.25, thank you, Jerica, for catching my writing error. These 3 numbers do form the sides for a right triangle. Same directions. Using a marker board, figure out, is it possible for a right triangle to have these 3 side lengths? All right, so looking at it, leg squared plus leg squared equals hypotenuse squared. 81 plus 1600. And 41 times 41 is 1681. Yes, it works out. And it's a bit interesting because then we get a third Pythagorean triple. 9, 40, and 41, all as whole numbers. Kind of weird numbers, but they will check out. So far, each of our problems that we've been focusing on have looked at, is this thing a right triangle, yes or no? Is it a right triangle, yes or no? Is it a right triangle, yes or no? Well, the converse of the Pythagorean theorem actually allows us to go further. Not just is it a right triangle, but what kind? We can figure out if it's an acute triangle or an obtuse triangle as well. The basic idea behind our work, and I'm going to start with a picture so that we can understand why this stuff works instead. Think about having a leg and a leg drawn together at a 90-degree angle. If we had to connect these pieces, it would be possible to actually go through and measure how long that is. Consider what would happen if this piece were actually too short. If the 20.1 was actually not long enough. What would you have to do to close up the gap? Keeping in mind that we can't make any side length longer because we have to use these 3 lengths. What would have to be done to close up the triangle? The shape would have to change so that we wouldn't have the 90. In particular, we'd have to bring this piece over and swing this part over as well so that they wound up meeting over here. It wouldn't be 90 anymore. What kind would it be? In this instance, since we shrunk down the 90 to something smaller, we've instead created an acute triangle. This type of behavior will occur if you take the so-called hypotenuse, the longest side, if you square it, and it turns out to be less than the sum of the other 2 legs, this algebraic behavior will force the red geometric behavior. Similarly, if we come back and say, what if, instead of being perfectly equal to, the 20.1 was a little bit too long? If it's a little bit too long, we still don't have a triangle because triangles can't have any kind of an overhang. So what would we have to do to fix the overhang? This would have to swing downward more to match an 18 like this. Yeah, that's a pretty horribly crooked line, so, oh man. 20.1. Swinging over here. And then downward toward, like that. And it switched the colors on me. And so we would wind up with an obtuse angle. That behavior will occur if we wind up squaring the shortest side and it's bigger than the sum of the 2 short sides. In the green, that algebra forces the obtuse angle. So basically, when we're looking at this stuff, we have 3 possibilities. Less than, greater than, or equal to. And please notice the way I've written these. I have written them so that the c squared, the longest side, the supposed hypotenuse, that's on the left-hand side. Man, I can't seem to write down numbers today. 20.1 and 20.1. Can't go around changing numbers just because I like them. And so, once again, writing it up, if we wound up with c squared is less than a squared plus b squared, that will create an acute triangle. If we wind up with c squared greater than, that creates an obtuse triangle. And as we already noted with the Pythagorean theorem, if they're equal, it creates a right triangle. So basically, all we have to do is put the same information into the calculator. It's the exact same work as we were doing before. Leg squared plus leg squared, and we're comparing it to the hypotenuse squared. The only difference, though, is are we comparing it for equal, or are we comparing it for less than, greater than? That's all. So which one do we wind up with? Let's crunch our numbers and find out. What is 20.1 quantity squared? Using the calculator, Frankie told me it's 404.01. And we're going to compare that to 9.6 squared, which is 92.16 plus 18 squared. That's 324. So after taking 92.16 plus 324, those two things add up to 416.16. And now let's compare them. Do we have less than, greater than, or equal to? Because 404 is less than 416, this has to be an acute triangle. The converse of the Pythagorean theorem guarantees it. Let's go over another example for this. Which kind of triangle is this one? Acute, right, or obtuse? Where do we need to begin? We know that we're going to wind up comparing c squared to the sum of the other two squares. Thus, we're comparing 29 squared with 4.8 squared plus 28.6 squared. If we run over to our calculator, we can get 29 squared pretty quickly. That's 841. That number 841 needs to be compared to the sum of the other two legs, potential legs. So we'll take 4.8 squared plus 28.6 squared. Putting those together, 841. Because these are equal, this has to be a right triangle. And here's our last example. Just like the last two, we know that we have to compare c squared with the sum of the other two sides. Thus, we are comparing 14 squared with 9 squared and 12 squared. Fourteen squared equals 196. 9 squared is 81. 12 squared is 144. And so we're comparing 196 with 225. 196 is less than 225. Because it's less than, what does that tell us? It's an acute triangle. And we would be done. Yes, greater than would make it obtuse. So let's have an imaginary change in the numbers. If this wasn't 14, let's say it were 17 instead. Same type of problem, just with slightly different numbers. Well, in that instance, 17 squared would lead to the number 289. And 289, that would have been greater than, so the side lengths 9, 12, and 17, those would force us to create an obtuse triangle. Do you know what number would make it a right triangle? Don't you remember our notes a little bit ago? What sides did we have before? 9, 12, and 15 created a Pythagorean triple, so with legs of 9 and 12, we'd have to have a hypotenuse of 15 for it to be a right triangle. Shorter than that is acute, longer than that is obtuse. And thus we'll finish our discussion here. We've looked at the Pythagorean theorem's converse to figure out if a triangle is acute, right, or obtuse.